Hi everyone, I am John Iwan. I come from National COCOON University in Taiwan. Today the topic I want to present is a study for conditional diagnosability of Pancake graphs. And this is my outline. My talk will be divided into 5 parts. The first is abstract, and then is the introduction. Then I want to introduce some basic properties of Pancake graphs, PN. And the fourth is my main contribution, conditional diagnosability of PN. And finally, we'll give a simple conclusion. And this is my abstract. I want to introduce my main result, the conditional diagnosability of Pancake graphs, denoted by P of n. The result is not difficult to read. The conditional diagnosability of Pancake graph P of n under the BMC model equals to an minus 21, denoted by T for C of P of n equals an minus 21 for n at least 5. And now we go to introduction part. Our basic motivation is, why do we need for diagnosis? The answer is that as the VLSI technology developed, a multiple sensor system may contain hundreds or even thousands of processors, and some of which may be faulty when the system is operating. So we need fault diagnosis. So here we need to define some terms. The first is diagnosis, which means the process of identifying faulty processors. Then we need to evaluate the diagnosis of the system, which is the diagnosability, which is defined to be the maximum number of faulty processors the system can guarantee to identify. These two terms are very important. In our work, we use the BNC model as our diagnosis model. Now we introduce the BNC model, which is developed by the 3 scholars in 1967. In the BNC model, adjacent processors are capable of performing tests on each other. Suppose there is an order pair UV represents a test performed by U on V, and the test result is recorded by either 0 or 1. We can see that when the test processor U is faulty, the test result is unreliable. Otherwise, the test result is reliable. Now we want to introduce some basic properties of Pancake graphs, P of n. And in an n-dimensional Pancake graph P of n, each node is assigned with a label with a permutation of n symbols. For example, in the following figure, it is a four-dimensional pancake graph P of n. And we can see that in each node is labeled with a permutation of four symbols. Next, each node, as we say U, equals S1, S2 to Si minus 1, S of I, Si plus 1 to Sn is adjacent to the node V equals to Si minus 1 to S2, S1, Si minus plus 1 to Sn. The previous I bit is the revision of the first I bit of the original node U. Now we come to see some interesting properties of pancake graphs Pn. In property 1, first we can see that Pn is n-1 regular with n-factorial nodes. Next, the connectivity of P of n, denoted by kappa of P of n, it is equal to n-1. Third, the girth of P of n, denoted by girth of P of n, equals 6 for n at least 3. The fourth is that the common edges between each subpancake graph between any two subpancake graphs equals to n-2 factorial. Next, and interesting is lemma 3. We see that the pancake graph P of n, where n is at least 3, has unknown distant 6 cycles of canonical form C/6 equals denoted by R3, R2, R3, R2, R3, R2, and each node of P of n belongs to exactly 6 cycle. And lemma 4 and lemma 5 describes some properties after deleting a number of nodes in pancake graph Pn. Lemma 4 states that let T be a node subset of P of n, where T, the number of nodes in T, is at most 2n minus 5 for n at least 4. Then Pn divided T has a large component and up to one trivial component. The large component is depicted by the green color here. And now lemma 5 describes that let T be a node subset of P of n, where T, the number of nodes in T is at most 3n minus 8 for n at least 4. Then Pn divided T has a larger component and up to 2 trivial components. And now we come to see our main contribution, which is the conditional diagnosability of pancake graph denoted by P of n. We have introduced some useful properties of pancake graphs. which will be used as a useful tool to solve our main problems in computing condition diagnosability. Now first, we want to define new terms. We say that our for set F is said to be a conditional for set if for every node U in a graph G, the neighbors of U are not all belongs to the for set F. Then we say that this set F is a conditional for set. Next, in definition 2, we want to define what is called the conditionally T-diagnosable. Definition 2 describes that a system G is called conditionally T-diagnosable if or only if, which means which to mean for any two conditional for sets F1 F2 and F1 F2 are not equal, and the size of F1 is at most T and the size of F2 is at most T, then F1 and F2 are distinguishable. If the system G satisfies such property, we say that the system is conditionally T-diagnosable. A similar definition equals to previous definition 2, which describes as Lemma 7, which defines that a system is said to be conditional T-diagnosable, which means for any two conditional for sets F1 F2 and they are indistinguishable, it will imply the size of F1 is bigger than T, or the size of F2 is bigger than T. We use this lemma in addition to definition 2, we use this lemma 7, to solve the conditional diagnosability of En. Now here we want to use a term to measure the fault diagnosis of the system, which is we call the conditional diagnosability of G, which is denoted by TC of G, which is defined to be the maximum value of T such that a graph G is conditionally T-diagnosable. So, lemma 8 describes a simple conclusion that for a system, the conditional diagnosability of a system G is bigger or equal to the traditional diagnosability of the system. In lemma 9, which is developed by Light Scholars in 2005, which states that consider two for sets F1 and F2, and F1 is not equal to F2 between two conditional for sets in the system G. Denotes S to be G divide F1 union F2. Then we have the following two observations. The first is if a node U is located in the symmetry difference of F1, F2, then the node U has two neighbors. One is located in F1 divide F2, and another one is located in F2 divide F1. The second observation is that if a node U is located outside F1 and F2, then the node U must have a neighbor both outside F1 and F2. Next, we see another tool, Lemma 10, which is developed by Scarlett John in 2013. In this lemma, let G be a system with girth, means the minimum cycle of a graph G is at least 6. Let F1 and F2, where F1 is not equal to F2, be two conditional force sets in the system, and they are indistinguishable. Also, let the term T to be the intersection of F1 and F2. Then G divided T has a component big H with the following 4 observations. The first, the vertex set of H is located in the intersection of F1 and F2. Second, the minimum degree of H is at least 2. Third, the number of vertices set in H is at least 8. And the last, the component H contains a subpath which contains 8 nodes. The subpath is depicted as the following this figure. We now come to describe our main theorem, which is divided into 2 parts. The first part, we consider the upper bound of the conditional diagnosability, which is described as the following lemma 11. In lemma 11, which states that the conditional diagnosability of the Pancake graph Pn is at most an minus 21 for n at least 4. The idea of solving lemma 11 is that we can construct F1 and F2 according to the definition of conditional diagnosability, such that the system is not an minus 20 conditionally diagnosable. So to construct F1 and F2, we consider a specific A cycle, and the F1 and F2 are we can consider the the neighbors of such a cycle so that F1 and F2 are indistinguishable. So if these two indistinguishable four sets are found and each of those size is an minus 20, then by definition we can realize that the conditional diagnosticability of P of n is almost an minus 21. So here we can complete the upper bound part of this lemma. Next, we consider the lower bound of the conditional diagnosticability. By the previous definition, we can only consider the following lemma 12. In 12, we consider F1 and F2, and F1 is not equal to F2 be any two conditional force sets, and they are indistinguishable in the Pancake graph. Then we only need to prove that the size of F1 and F2 are both at least an minus 20. To sketch the proof, we can consider the intersection of F1 and F2, denoted by big T. So here we can consider the size of T. If the size of T is biggest enough, then the size of F1 or the size of F2 are either to be bigger than an minus 20. So we can finish the proof of bigger T. For the cases when T is smaller, the analysis is much complicated, and because of the time constraint, we omit its detailed proof here. So by combining the previous lemma 11 and 12, we get our main theorem. So in theorem 1, we realize that the conditional diagnosticability of the Pancake graph Pn equals to an minus 21 for n at least 5. And now is the conclusion. And in the table, we can consider many interconnection networks considering conditional diagnosticability, and the conditional diagnosticability are collected in this table. The final line is our contribution in Pancake graph. We see that the conditional diagnosticability of Pancake graph is an minus 21 for n at least 5 under the PMC model. Thank you for your coming and listen to my presentation. Thank you.